Today we're going to learn how to use rice tables with grams. Previously we've used rice tables to do limiting reactant problems, but we've never used rice tables when we began the problem with grams. And most of the times chemists, or actually all the times chemists, are actually going to mass things and use grams when they do problems, so this is actually the most appropriate. So our objective is to distinguish on how to use a rice table with grams to determine the limiting reactant, the excess reactant, and the amount of product. So just a quick refresher, remember that a limiting reactant is defined as the reactant that limits the amount of other reactants that can combine. The amount of it also determines the amount of product that can form in a chemical reaction. It's also sometimes referred to as a limiting reagent. Related to airplane flight. Excess reactant, substance not completely used up in a chemical reaction. So let's say we have a plane with 350 seats. There's 400 passengers. It can hold 400 passengers. But if you have 400 passengers, that's too many, so that would be the excess. So passengers would be excess, and the seats on the plane would be limiting. So those 50 passengers who don't get to get on the plane, sorry about that, 50 passengers who don't get to get. So the 50 passengers who do not get to get on the plane, that would be the amount of product produced, and so they are also the excess, and the plane is the limiting. So let's do an actual problem here. We're going to do two problems. The first one, we're going to do a refresher with moles. Let's say you start with a reaction. Here's your R for the rice table. The reaction is carbon plus oxygen gives you carbon dioxide, the stuff we breathe out. You start with 5, and this is a nice simple 1-to-1-to-1 ratio. So this will be easy to do without doing any ratios. As far as ratios to determine the other products, you start with 5 moles, 10 moles, and we see that 5 moles would be our limiting. We have extra moles of O2, so the limiting is going to be used up first. The amount of product we would get would be 5 moles of CO2. So at the end we have product and reactant left over. We have excess oxygen or O2 left over. So we have that as an example. So let's do a before and after chart. So I'll call it rice reaction. Initial amounts, step 1, the moles that are present before it starts. So we'd have 5 moles and 10 moles. So I think everybody knows that what would happen during. We also referred this as the initial amounts will be here. During, we refer to this as change, and after, we call that the end. So, and we also, as far as carbon dioxide, there's none of that in the beginning, so we'll just put 0. And then we know that there's 5 moles are the limiting, so that's used up completely, so that goes down by 5. It's a 1-to-1 ratio, so the amount of oxygen that is used is also going to go down by 5. And we see that 1-to-1 ratio there, so oxygen decreases by 5 as well. That's minus 5. And then the carbon dioxide goes up by 5 as well, because it's still a 1-to-1 ratio. And when you say 5 minus 5, there's 0 carbon left at the end. 10 minus 5 gives you 5 moles of O2 at the end. And then, so carbons are limiting, oxygens are excess, and then we see also, let's go back to the second, we see the amount of carbon dioxide would be produced would be plus 5 here, and then you have 5 moles at the very end. So let's do a problem with grams. That's what we're here for today. This is the first problem. Let's say we have 2 moles of HF are exposed with 4.5 moles of silicon dioxide, which is limiting reaction. So this is our R right here. This is our R for our reaction. Let's start. This is our R for our reaction. This is our first problem. So we'll start with our R for our reaction, and then the mass is not given, so we know moles this time. We have 4.5 moles of silicon dioxide, and then we also have 2 moles of HF and 0 moles of the other 2 to start. Both of these would be 0 amounts, and 4.5 and 2. And so the B for us would be the initial, and then the silicon dioxide goes down by 4.5. The HF goes down by, there's a 4-to-1 ratio, so that goes down by 18. And we know from that that what actually is limiting is the silicon dioxide, and so we end up with minus 16. Now this wouldn't happen if you've done it this way. You've got a negative number, so you know that you've not determined the limiting reactant correctly. So this tells us that HF would have to be the limiting reactant. So you have to start over. So to do this, you want to actually say that HF is the limiting, so that goes down by 2. That gives us 0 of that at the end. Then you go to the other reactant. It's going to be a 1-to-4 ratio, so you're going to divide 2 by 4, so it'd be 0.5, so it goes down by 0.5. And so at the end we have 0 moles of HF and 4 moles of silicon dioxide, SiO2. And that's a limiting, and so that's how we did that one. Now let's do a sample problem, and we're going to do this one with grams. So let's first, okay, the black oxide of iron, Fe3O4, occurs in nature as a mineral magnetite. This substance can also be used in the laboratory by the reaction between red-hot iron and steam, according to the equation below. So you have 36 grams of water, and it's mixed with 167 grams of iron, which is a limiting reactant. We also know what is a mass of the black iron oxide that is produced. So when we do this, we see that, and we also know what is the mass of the excess reactant that remains when the reaction is complete. So what we want to do is start with our mass, and we know that the mass of the water is 36 grams. The mass of the iron is 167 grams. Now to do a rice table, what we're going to have to do is change both these to moles. So we'll do that. So we'll change that to moles, and we end up with divide each by the molar mass. The moles of iron is 2.99. The moles of water is 2. Now we know the initial moles, the other 2 is none as reactant, so these 2 would be 0 initially. And then let's fill out our rice table at this point. So we know that the initial amounts of those 2 we'll put in, that would be the initial. The initial amount of iron is 2.99. The initial amount of water is 2.0. And what we do is a mole ratio for both of these to the product to determine what the limiting is. So you'd have to multiply to find what the limiting for the water. You'd multiply. We're trying to find iron, so basically you divide this by 4, because you're going from water to iron the iron oxide compound. And so when you do this, you're going to divide this by 4, and that would mean you'd produce 4 moles of FeO3 going from the water to the iron. Now if we go from iron to the iron oxide compound, we'd multiply the 2.99 to go there. We'd multiply that by 1/3. And if you multiply that by 1/3, you're going to end up with approximately 1. And when you multiply this by 1/4, you end up with 1/2. So that should tell us that the water is the limiting. And so this number right here, the 2 moles, is going to determine how much the iron goes down. It determines everything, basically. It determines how much the water is used, which is all, since it's limiting. Determines how much the iron oxide compound is produced, and how much of the water, or the hydrogen, is produced as well. So what happens? It's limiting, so every bit of the water is used, so it goes down by -2. And then also, you use this 3-to-4 ratio. What you're trying to do is the ratio of water to iron. There's 4 waters for 3 irons, and you're multiplying the 2 by 3. 2 times 3 is 6, divided by 4 gives us minus 1.5. And so 2.99 minus 1.5 gives us 1.49. So those are the amounts we have there. Now also you see for the amount of hydrogen that is produced, it's the same ratio as hydrogen and water. So the amount that the water goes down is the same as the amount as hydrogen goes up, because it's a 1-to-1 ratio. But instead, you're adding that to 0, so you end up with 2 moles of hydrogen at the end. Now the other thing you want to do, so we know that's of course a limiting reactant. We know of course that the iron is the excess reactant. Now the other thing we want to do is to change the water to the iron oxide compound. Now to do that, we use a 1-to-4 ratio, and that gives us 0.5 moles. We did that previously to determine the limiting reactant. So that gives us the amounts that we have here. So the excess reactant, of course, we go back to that as iron. So the initial amount of iron is going to be 0. There's none. And then what we do is we basically add 0.5 to that, because when you multiply 2 times a 1/4 ratio, you get plus 0.5. And so that goes up by 0.5, and you end up with 0.5 at the end. Now we have one more step here. We have to change that to grams. And so what you're going to have to do is use the molar mass here of the iron oxide compound to get that to grams. So that's the final step. I'm just going to go quickly through these, place all these in here again, and what I want to show you is the last one. And in this last one, what I did is I used this 0.5, I multiplied that by the molar mass, and that gave me, from this we can get the mass of the iron oxide compound that's produced. So we get 1.49, you multiply that by the molar mass, which is 55.85, and this would give us the grams of iron. So that would be the mass of iron that didn't react. And then up here we have this would be the amount of iron oxide compound that's produced. So we've got both numbers. We've got the mass of the iron oxide compound that's produced and the mass of the iron that did not react. So now we've used grams in a mole or a rice table with moles, and we've accomplished the same thing we've done previously. If you have any questions, let me know.